In this video, we are going to learn implicit differentiation. And so in this first example, they are asking us to find the derivative for the variable y related to the variable x, dy dx. So what this means is that as long as we're deriving with variables respect to x, it's normal. But if we're deriving a variable y, we have to multiply it by whatever the derivative of y would be with respect to x. So let me show you. So as we approach this problem, as long as the term is in terms of x, you just derive like normal. So we're going to pull the 3 to the front and multiply, so that becomes a 24, and then decrease the power by 1 times x squared. Okay, so when we get to a term that doesn't have an x, we will go ahead and derive it. So we're going to pull the 3 to the front times the 4, so that becomes a 12. And then decrease the power by 1, so that becomes y squared. But because we don't know what the value is of y in terms of x, we automatically multiply by what we call a dy dx. And then equals the derivative of the 2 is just 0. Now, you have to, we don't need the equal sign there. You have to get the dy dx by itself. So you're going to use your algebra to do that. So what I'm going to actually do first, I'm going to add the 12y squared times the dy dx to both sides, so that I've got positive terms. You could have moved the other one as well, and then you would just have negatives. So, but basically I've got a 24x squared that is now equal to a positive 12y squared times the dy dx. And so since we're trying to figure out what the derivative of y is with respect to x, in other words, we're trying to solve for this variable here, since it's being multiplied by the 12y squared, we're going to divide both sides by 12y squared. So 24 divided by 12 would leave me with a 2 on top. X squared is on top. And then on bottom I have my y squared. And so now we have solved for dy dx. And this is what they're looking for right there. Okay, so same thing in the next question. But again, to make it easier on me when I get ready to take derivatives, I'm going to first rewrite these radicals. So this first term I'm going to rewrite as a 5 times x to the 1/3 power, since it has a cube root. Minus, I'm going to rewrite this as a 2 times y to the 1/2 power, since it has a square root. And then it's equal to 2. Now, once again, we are looking for the derivative of y with respect to x. So as long as we're deriving x's, we just derive like normal. So here we go. Pull the power to the front and multiply. That becomes a 5/3. Decrease the power by 1. So what you're thinking of is minus 3/3. So that becomes x to the negative 2/3. And we're done with that term. All right, on the next term, so we've got a minus. Pull the power to the front times the 2. So 2 times 1/2 would just be a 1. And you don't have to show the 1, or you can. It doesn't matter. And then decrease the power by 1, which is like saying minus 2/2. So that would leave you with a negative 1/2. But since this is not the variable x, you have to immediately say times dy dx. And then equal, the derivative of 2 is just 0. So once again, we have an algebraic expression, and we need to get the dy dx by itself. So once again, I'm going to move add the y to the negative 1/2 term. I'm going to add that to both sides. So plus y to the negative 1/2 dy dx. And then, so let me first rewrite what we've got here. So 5/3 x to the negative 2/3, and that's equal to y to the negative 1/2 times dy dx. And now, in order to get the dy dx by itself, it's being multiplied. We'll divide both sides by y to the negative 1/2. And because they don't want you to leave negative exponents in this particular answer, what we're going to do is the variables that have the negative exponents, we're going to flip them. So right now, the fraction 5/3 means I've got a 5 on top, a 3 on bottom. X to the negative 2/3 would put the X on bottom, and once you do that, it's a positive 2/3 power. Y to the negative 1/2 would bring the Y term to the top, and once you do that, it would be a positive 1/2 power. So there is my dy dx. All right, last but not least, this time notice we're looking for dy dt. That means we're going to derive everything with respect to the variable t. So if another variable is there and it doesn't have a t, we have to multiply by the derivative of whatever that variable is with respect to t. So let me show you. So we'll take the power of 4, pull it to the front. 4 times 3 becomes 12. Decrease the power of x by 1. So that's an x cubed. Because this is not my variable t, I have to say times dx dt. Because I don't know what variable x is. With respect to t, I have to multiply by the derivative of whatever x is with respect to t. All right, then I'm going to continue. So do the normal derivative. Pull the 3 down. 3 times 5 is 15. Decrease the power by 1. That's a y squared. And again, since this is not the variable t, we have to say times dy dt, because we have to know what the derivative would be of y with respect to t, and then equal the derivative of 8 is 0. Now, in this particular problem, they're asking me to find dy dt. So this is what I want to get by itself, which means algebraically I'm going to add this whole term to the other side, or to both sides. Okay, so it cancels there. So I've got a 12x cubed times dx dt, and that is equal to a 15y squared times dy dt. And again, I'm trying to get that dy dt by itself. So since it is being multiplied by 15y squared, I am dividing both sides by 15y squared. And then 12 over 15, that will reduce. Both of those are divisible by 3, so that would leave you with a 4 over 5. And then you still have your x cubed, you still have your dx dt on top, and then on bottom you still have your y squared. So that would be my final answer.